Have you ever stopped to think about how we predict the behavior of something as wild and chaotic as a gas? For the longest time, we had this beautiful, simple, well, perfect model. But as it usually does, reality turned out to be a little more complicated. So let's get into the story of how one brilliant insight took us from a perfect idea to a much, much more powerful reality.
It really all kicks off with a simple question. What happens when you squeeze a gas? I mean, you'd think it just gets smaller and smaller, right? Forever. But we all know that's not the whole picture. Eventually, something really cool happens. And our first, and for a long time, our best model for gases, well, it couldn't explain it at all.
To see why, we've got to start with that first model, the ideal gas. I want you to picture a world full of these tiny, perfect billiard balls just zipping around, bouncing off each other without a single care.
Now, this idea is all wrapped up in what we call the kinetic theory of gases, and it makes a couple of really big assumptions. First, it says the gas particles themselves are just points in space. They have zero volume. And second, they don't interact with each other at all. Unless they have a perfectly bouncy collision, they just fly right past one another, completely indifferent.
And from these super simple assumptions, we get this incredibly elegant and famous equation, the ideal gas law. And for a long time, it was a fantastic tool. It worked especially well for gases at low pressures and high temperatures, where those assumptions are almost true. It's simple, it's powerful, and it's useful. So, what's the problem?
Well, as scientists started pushing the boundaries, they found a pretty big crack in this perfect model. It worked great, right up until the moment it didn't.
And here is the absolute deal breaker. The ideal gas law completely fails to explain one of the most fundamental properties of matter. See, if you squeeze an ideal gas, the model just says it gets denser and denser forever. It never turns into a liquid. But we know real gases, like the very air we're breathing, can be liquefied. Our perfect model was missing a massive piece of reality.
So, this is where our hero steps onto the stage. A Dutch physicist named Johannes Diederik van der Waals. He looked at this problem and realized the elegant model didn't need to be thrown out. It just needed a couple of really clever tweaks to bring it back in line with the real world. And get this, he did it in his 1873 doctoral thesis. I mean, that's just incredible. He wasn't just fiddling with an equation, he was fundamentally challenging the core assumptions everyone had been using for decades. He basically argued that to understand real gases, we had to stop pretending they were perfect.
Van der Waals' fix went right after the two big simplifications of the ideal model. He said, first off, these particles aren't just points, they have real actual volume. They take up space. And second, they aren't indifferent to each other. There's actually a slight attractive force gently pulling them together. He then turned these ideas into two mathematical corrections. The B term basically says, hey, the molecules themselves take up space, so the volume the gas can actually move around in is a little less than the total volume of the container. And the A term accounts for those tiny attractions, these cohesive forces, which means the pressure the gas pushes on the walls with is just a little bit less than we'd expect. And with these two honestly pretty intuitive fixes, van der Waals created an equation that completely changed our understanding of both gases and liquids forever.
And there it is. Look, it looks a lot like the ideal gas law, doesn't it? But you can see his two tweaks right in there. The pressure, P, gets a little nudge from that attraction factor, A. And the volume, V, gets adjusted by the particle volume, B. It's not a replacement, it's an evolution of the original idea.
And this is the magic. This is the whole reason we're talking about this. This single, slightly more complicated equation could do what the ideal gas law could never, ever do. It could model a substance as a gas, it could predict the exact conditions when it would turn into a liquid, and it could even describe its behavior once it was a liquid. It was a bridge between two states of matter.
The impact was just immediate and profound. You don't have to take my word for it. The legendary physicist Ludwig Boltzmann himself paid van der Waals the ultimate compliment, calling him the Newton of real gases. I mean, that tells you just how big of a deal this was.
And for this amazing work, which all started with his thesis decades earlier, Johannes Diederik van der Waals was awarded the Nobel Prize in Physics in 1910. It was this incredible recognition for taking a perfect idea and making it real.
So look, this isn't just a fun story from science history. The van der Waals equation unlocked a whole new world of possibilities, and its influence is absolutely still felt today. I mean, this model gives scientists the theoretical roadmap they needed to finally liquefy even the most stubborn gases, like hydrogen and helium. That breakthrough alone opened up the entire field of low-temperature physics. It became a cornerstone of modern thermodynamics, and it is still a critical tool for engineers who have to manage real fluids in everything from pipelines to power plants.
So when you boil it all down, this story is about so much more than just a clever equation. It's a perfect example of how science actually works. We start with a simple, elegant model. We test it against the real world. We find where it breaks, and then we refine it, making it a little more complex, sure, but a whole lot more powerful.
And that kind of leaves us with a really fascinating question to think about, doesn't it? In science, in economics, even in the way we think about our own lives, what other ideal models are we using right now that are just waiting for a couple of clever tweaks to unlock a much, much deeper understanding of reality?